Okay, so this video will be about the first three sections of Chapter 2, the chemical context of life. And this is a list of all of the terms that are included in these first three sections. If you want to pause the video for a second so that you can get all of the words. These are all the things that I will go over, and I'll be drawing a lot of things. So you want to have your markers and some paper out so that you can draw some of these concepts. All right, so the first thing I'm going to talk about is elements and compounds. And if you were in class, you should have learned about some of these, but for the most part, it's very simple. You have your elements, and they are the items that are located on your periodic table, and they're made of only one type of atom, so they're very pure. And if you look at your periodic table, there are over 100 atoms or elements represented on the periodic table, but only 92 occur naturally. So you can find them on Earth, and some of the other ones were created by man. They're very temporary. Some of them have lasted a little while, but some of your larger atoms are simply synthetic, which is man-made. All right, when you look at an element and you look at the parts of it, you're going to have an atom, and then the center of an atom is a nucleus. Okay, and the nucleus is packed very tightly with protons and neutrons. Protons always have a positive charge, and neutrons have no charge, so they're considered neutral. So when you look at the atom, the nucleus, the center of it, is going to always be positive. So we have it here. We have our positive protons in here, and we have our neutral neutrons, okay? And we're going to talk about what the number means and those kind of things. This is just a little bit of review from chemistry. Then around the nucleus, on different pathways, they're actually very three-dimensional. So it would be like a balloon inside of a balloon inside of a balloon. These pathways aren't just circular. They can run in 3 dimensions. You have little places for electrons to run. And electrons are always negatively charged. And so that's why they don't go crazy and leave, is because they are attracted to positive, because we're going to learn a lot of things happen in our body and a lot of things happen in organisms because negatives love positives. So that first little path, that first little zone that they can move on is kind of tiny because it's close to the nucleus. So it can only hold and has room for 2 electrons. But every other one after that will be able to hold 8. And they're all configured in different ways, and we don't need to know that. And they can go on and on and on, the bigger the atom gets. But the only ones we really care about are the ones on the outside. So this outside shell is called our valence. And any of the electrons that travel on it are called valence electrons. Now, all the other electrons in here are important, but the only ones that actually determine how that atom behaves are the ones on the valence. Ooh, not a good marker. So the ones on the valence also determine what group your element is in. Okay, so this determines behavior. Okay. Now, the reason we want to discuss this is because we want to talk about bonding. And bonding is one of the most important things that's going to happen in all organisms, and it's bonding between different atoms. So in your body, we'll back up a little bit and we'll talk about the elements that are essential. Carbon, hydrogen, oxygen, and nitrogen, okay, represent together 96% of all living organisms. So if you look at the trees, if you look at the people, If you look at the snail, if you look at the, I don't know, mosquito, everybody loves him so much. It's a beautiful mosquito. All right, if all living things, okay, even down to the little bacteria, they are going to be composed of carbon, hydrogen, oxygen, and nitrogen. Now, the most abundant of all of these is oxygen, okay? And so in your body, oxygen represents 65% of you. Now, it's not just, you're not just filled up with an oxygen gas. Oxygen combines with lots of other things and creates compounds. So, oxygen can be found in the form of CO2. It can be found in the form of O2, which is two oxygens bonded together. It can be found in H2O. It can be found in C6H12O6. So, et cetera, et cetera, et cetera. When I say your body's composed of 65% oxygen, I mean that most of it is going to be bound in some sort of molecule. So these are just little bricks, but in order to build a house, you got to put all the bricks together. Carbon is going to represent 18.5% of all living things. Hydrogen is 9.5%. It's a very tiny little atom, but it's very highly represented. And then nitrogen's at 3.3%. Now, the other 4% stands for trace elements. So 3.7% of that remaining 4% is going to be calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And so all of these are necessary in teeny tiny amounts. The most is going to be calcium, about 1.5% of your body. And I know most of you think that's going to be found, necessary for your bones, but it's actually necessary for muscle contractions. So your bones store it, but you also need it for muscle contractions, and you also need it for nerve impulses. So just about everything you do is going to require calcium to be involved. Sodium and potassium are involved in the sodium-potassium pump and muscle contractions. Magnesium is good for your skin and hair and nails. Chlorine comes in the form of sodium chloride, which are salts. So you're going to have all kind of elements in your body, and then you have because these are in such tiny amounts. These are your essential, both of them, but these are just in tinier amounts. Then we have something called trace elements. Right, and trace, TRA, that's a C. Trace elements mean that they are essential, but in small amounts. Right, and so when you are looking at the percentages represented in your body, it's tiny, and so it make you think they're really not significant. But if you don't have them, you would die. And one of the ones that should kind of be the most obvious is iron. Okay, iron is chemical symbols Fe, and it's used, your hemoglobin needs it to help carry oxygen and carbon dioxide. So we should all know at this point that if you don't have oxygen in your body and it's not getting carried anywhere, it's not going to be good. You're going to die. Okay, so we need to have iron, but your body only uses needs less than 0.01% of your body is iron. So even though it's tiny amounts, its job is huge. So all of these you're going to find are basically what you're built from. So your muscles, your bones, your skin, your hair, your nail, your tendons, your ligaments, all your organs. These are like the big bricks of your house, and the boards and all the things that your house is built of, if we were comparing your body to a house. But all of these things are the little tiny details that are super important. And the big part is good, but the little tiny details are also necessary. So back to our discussion of elements. We sidetracked for a second, and we talked about some of the essential elements you needed, and then we also talked about some of the parts and pieces of an atom. And so we did the protons and the neutrons, and then we talked about the electrons. Okay, and these are all called subatomic particles, because that means they are tinier than an atom. So the subatomic particles are protons, neutrons, electrons, and then there's quarks and all these other things, but we don't want to get that tiny. We're just really focusing on the electrons here, and we're especially focusing on the electrons on the valence. All right, when elements are hanging out all by themselves as single atoms, they are not stable. Okay, and their whole game plan is going to be to get stable. And when we're talking about elements, stability comes in how many electrons are on your valence. Magic number of electrons on the valence is 8. Okay, and when you have 8 valence electrons, no matter how many you have before that, we're only talking about that last level, you want to have 8. And when you have 8, you're happy. So when we look at a periodic table, the periodic table is arranged to help us understand how many valence electrons all of these different elements have and who they would most likely bond with, and if they bonded with them, how they would form a couple. So bonding is basically elements looking for stability. And so everything in this whole group 1, they all have different numbers of electrons, but they are all put in group 1 because every single one of them has 1 valence electron, and that means it is 7 electrons away from being stable. They stress, okay? So they're definitely looking for a partner because they are way far away from being stable. Everybody in group 2 is put in this column because they all have 2 valence electrons. They're closer to 8, but still pretty far away. All of these in this little dip are called transition metals. And the word transition means they change. So basically, some of them can have 2 on their valence, sometimes they have 3. But these are all 2 to 3 valence electrons. But we're not gonna completely identify them because they have a little variety to them. Then group 13, they have 3 valence, so we call them plus 3s. And then this group right here, group 14, and they are represented by this top element, this carbon, and this is super important. They have 4, and we call them plus or minus 4, because 4 is like dead in the middle. You're not like so far away, but you're not so close either. You're right in the middle. So you could either give away 4 and become more stable, or you could gain 4. So it makes carbon a very versatile atom. And then as we get further this way, these we call minus 3s because they actually have 5 valence electrons. So they just need 3 more. We call these minus 2s because they have 6 valence electrons. So as we get closer and closer and closer over here, these elements are getting more and more and more full. They're not stable yet, but they are super close. And then group 17 has 7 valence electrons, so we call them negative 1 or 1 negative. So here, I'll go back and label these. So these have 1 valence, 2 valence, 3 valence, 4 valence, 5, 6, and 7. So then you look at this last group. This last group, you will never see them form any bonds because they don't have to. What's special about them? They all have 8, okay? So they are stable. Therefore, they do not need any other element to help them be stable. Everybody else on the periodic table is looking for a partner and looking to bond and looking to join up to become stable, but group 8 is not. And these are called the noble gases. And they're noble gases because their stability and they're kind of snobby. All right, they don't need anything else. But now, looking at the way this table is set up, you should be able to understand why the 1s over here love to bond with the 7s over here, because 1s and 7s equal a match made in heaven. That gives you that perfect happy number 8. 2s and 6s like to join together. But every now and then you can get a 1 that bonds with a 6. It's just that 2 of them have to come over here and bond with one of those, because 2, if you have 2 of them, it's a 1, 2, and then you have a 6. So everybody's looking for the perfect number 8, right? When we do this, when we bond that way, these are called ionic bonds. And the reason they're called ionic bonds is because everything on the left-hand side of your periodic table is usually called a cation, okay? And they're called cations because they're positive. They like to give away electrons because basically their valence would be happier if they gave away. They only have like 1, 2, 3. Over here on the right-hand side of your periodic table are your negatively charged ones, because they're so close, they just need a few more. And we call them anions, okay? Cation is positive, anion is negative, and they would like to take electrons, okay? And so that's where you get the, over here are all your cations, over here are all your anions, and then you have your little step in between. And along that line, that's kind of like your dividing line, the north and the south. But we call the ones that touch it metalloids because sometimes they act like a positive. And these are all metals. So everything on this side is considered a metal, and everything on this side is considered a non-metal. Okay, so most of what you're going to find in your body is going to be non-metals in big amounts. So our carbon, nitrogen, oxygen, and then hydrogen. He's the wild card. Those are your 4 main elements that you have in your body. And then after that, calcium is one of your 4%. Phosphorus is a 4%. Potassium is a 4%er. They're not all 4%, but they're in that range. Sodium, chlorine, magnesium. Where's my magnesium? Okay. And so these are going to be, these hot pink ones are going to be that other 4%. So your body's basically built of 4 main building materials and then 7 supplementary materials. Then your trace elements that are necessary for life are going to be, like I told you, iron. That's found in there and you need to have it, but not in huge amounts. And then we have boron. You only need about a teeny tiny amount of that. You need a little bit of chromium. You need a little bit, there's chromium. You need a little bit of cobalt. You need a little bit of copper. You need a little bit of fluoride, or fluorine, excuse me. You need a little bit of iodine. You need a little bit of iron, which I've already highlighted. You need some manganese. You need some molybdenum. Where are you? Okay. You need selenium. You need silicon, Si. You need 10, Sn. There's silicon. You need vanadium and you need zinc. Okay. So most of your stuff is you get all your metals here, and your metals are going to help. These are all called your electrolytes because they're charged particles, and these are all the necessary elements. But your bright yellows here, ignore your noble gases, are your 4 main ones. Your hot pink ones represent the other 3.7%, and then your orange ones represent that 0.3%. So with your ionic bonds, we call them ions because it has the word in there, ion. cation, anion, okay? Ion means charged particle. Remember, these two are bonding and joining up so they get that perfect number of 8. And that's called your octet rule. Okay? But sometimes that's not possible. The positives and the negatives can't get together. So another type of bonding has to occur. And this type of bonding is going to be when atoms share electrons. So everything over here on this side, this is going to be your non-metal side. When they form bonds, they can't give and take because they're all so very close to being that perfect 8. And so instead of bonding with something that's going to give them electrons, they will work together and share electrons. So they'll create covalent bonds. Co means to share. Valent, so they're sharing electrons on their valence. Okay, so they share electrons. And the whole goal is to have 8. Okay, and the basic deal is if they share, then they both have equal, I guess, possession of the electron. So if they're sharing 2, then they don't consider it one or the other. They consider it, if you count, it belongs to both. So these are all going to be nonmetals, okay? And they're still bonding to be stable. So if we are ranking bonds right now, your ionic are going to be your strongest chemical bonds, and then covalent will be second, but it'll be a very close second, okay? And they are chemical bonds. So they are marriage bonds. They are meant to stay together, and the only way you can break them apart is by burning or some other chemicals and have some sort of chemical reaction. So they'll basically stay together, which is what you want in your body. Then we will learn about 2 other temporary bonds that don't chemically bond things together, but they almost are like the glue that stick them together. So you have your most common hydrogen bonds. And I'll show you some images of those in a minute. And then you have van der Waal interactions. And they are ranked in that order based on strength. So your hydrogen bonds are stronger than van der Waals, and your van der Waals are the weakest of all of these connections. So bond just means a connection. Okay? 1 and 2 are very permanent. 3 and 4 are temporary and can be separated and rebonded almost on a second by second basis, and we'll talk about what these are used for. Okay, so far, just to highlight what we have talked about, we have talked about elements, and we have talked about how they bond to form compounds, and therefore we've talked about our chemical bonds. We've talked about our ionic bonds and how cations and anions form together. We've talked about that it's based on like the valence shell, and valence electrons are the electrons that travel on that shell. Electron shells are just the pathways that the electrons travel on. We've talked about covalent bonds, about how they share electrons. When they form bonds, they create molecules. So atoms join together to form molecules. We've talked about your essential elements that you have to have. It's the 4 main ones, and then the 7 extra ones, and then all your trace elements. We've discussed the trace elements, and we've highlighted those on your periodic table. We've drawn an atom, and we've looked at protons, neutrons, and electrons. We're going to skip Dalton. It's just the way they measure the mass of an atom. Atomic number, mass number, atomic mass we'll go over. And then we did basically introduce you to hydrogen bonds and van der Waal interactions, but I haven't completely gone over it yet. Now, I do want to tell you that for salts, a lot of you, when you think of salt, you think about what you put on your meal shake it on there, and it is NaCl. But a salt in science is NaCl. NaCl is an example of one. But all molecules that form ionic bonds are called salts. So all molecules that form ionic bonds. So whenever you put a cation with an anion and you make an ionic bond and you get your compound, anything that gets made is called a salt. Okay, so that helps you out with that. All right, so let's finish off this list of things. We're going to go with, on your periodic table, all of your elements are nicely labeled in a box. And in the box, there's all kind of numbers. So I'm just going to basically deal with, I'll just show you one so you can remember it. But in there, you have your chemical symbol, and sometimes they have the name of it. Depending on the periodic table you have, sometimes they have the number at the top and then this number at the bottom, or they'll switch it up on you and they'll put this number here and this does this here. Doesn't matter, okay? Your smaller number always represents your atomic number, and your larger number represents your atomic mass. Okay, mass means a measure of how much is there, and your atomic mass is basically, should be called your nuclear mass. It's the mass of the nucleus. So it's the protons plus the neutrons. So that's how much that weighs. So if this number right here is always smaller, and it's just the number of protons. So basically, if that's your number of protons, whatever adds to that tells you how much the neutrons weigh. So in this example, your protons weigh 6 Daltons, and then your neutrons would weigh 6.011. Okay, lots of times they'll just round it to a nice clean number, and it's 6 protons, and then it's 6 neutrons, because we would round that to 12. All right, if you saw it with a larger element, we'll say Pb, which represents lead. Lead has 2 numbers in its box. It has 82, and it has 207.2. And I'll just round that to 207. And therefore, this tells me that in the nucleus of a lead atom, it has 82 protons. But also, this number tells me everything else in there for the neutrons. So you do 207 minus 82. You're going to get 5, 10, 2, 1. Okay, so 125. Now, that doesn't change the charge in the nucleus of that lead atom, because neutrons are neutral. It just makes it very heavy. And so with 82 protons, it has a charge of plus 82, which holds all these electrons close to its nucleus. And the cool thing is you can always determine how many electrons there are based on protons. Because if there's 82 protons, there are going to be 82 electrons. So if you go back here to carbon, you can guarantee yourself that if there are 6 protons, there are going to be 6 electrons. So the number is called the atomic number, and they say it's for number of protons, and it is, but it also is for number of electrons. And then the big number is called your atomic mass, or the mass number, and it just tells you how much the nucleus weighs, and then you can subtract them to get the number of neutrons. Now for radioactive sounds like a scary, dangerous thing, and sometimes it can be. But radioactive just means that sometimes atoms like to lose their electrons, or I should say not like to lose them. They actually lose them because of the way they behave. So protons in the nucleus are this very positive, and then all around these beautiful, ugly circles. These are all your orbitals that the electrons travel on. And they're negative, so they still have an attraction to this positive nucleus, and that's what keeps them in line. Some are over here, They're just all flying around, okay? And 2, and then 8, and then 8, and then 8, et cetera, et cetera, et cetera. Now, if you have a big, big, big atom, and it has like 78, 92, 110 electrons, those outer electrons on that valence are going to be so far away from the nucleus. All right, so when they're that far away, do you think there's as strong of an attraction from this electron with this proton? And the answer should be no. Okay, now magnets, they love positive and negative love each other, but if you pull a magnet away, if you pull it a short amount away, it'll snap back together. But if you pull it far enough away, there's not as much of an attraction because of distance. So large atoms can lose valence electrons, and when they do that, it's called radioactive. And we say that the process of losing that is radioactive decay. So as things decay in an atom, it's not like rotting or anything. Decay means they lose their electrons, and electrons are wildly full of energy. So if we were to happen to see this under some sort of scanning machine, this would actually light up. So as it decays, it lights up and it creates an electrical image. So some of you who have had some sort of imaging done, they actually use radioactive molecules. Okay, I'm going to show you a picture in your body, because they can't see soft tissue under an x-ray. But if they inject it with these radioactive isotopes, or these radioactive atoms, as these electrons move, they can pick up on the light. And in this situation, they attach these atoms that lose electrons very easily to a sugar molecule. And they injected it into a patient because they're trying to find if this patient has cancer. And so because cancer cells love sugar, the sugar goes straight to the tumors. And in this person, this image is the side of their head, and this is their esophagus and their throat. They have throat cancer. And it's because those sugar molecules, full of those radioactive isotopes that glow because they're constantly losing electrons, allows the doctors to see what's going on right here in this area. So that's why we talk about it in biology, because we do use it for diagnostic tools. Okay, so far, let's double check our list. We have talked about Dalton. Those are just the units for the mass. Atomic number, mass number, atomic mass, radioactive, and okay, we got a couple more things to talk about, and then we're done with these first 3 units. All right, so with isotopes, isotope, you just need to memorize the definition. It's atoms with the same number of protons, but they have different numbers of neutrons. Okay, now that doesn't really change much except for the heaviness or the mass of the nucleus, because the charge is here. Neutrons have no charge, so they don't change the overall charge of the element, and the element is determined, or the atom's name is determined by the number of protons. So if you change number of neutrons, not a whole lot of things change about how the atom behaves. So this has a proton number of 6, so this is carbon. And this also has a proton number of 6, so it is also carbon. But we actually call this one carbon 13, and we call this one carbon 12. And if you're paying attention, that's because the atomic mass, the protons plus the neutrons in this one is 13, and the protons plus neutrons here is 12. And so that number just tells scientists that this carbon has 6 neutrons, but this carbon has 7. So if I had carbon 14, then my proton number cannot change because it's carbon, so it has 6. But that means my neutron number is even larger, so it's got to be 8 neutrons. Okay, and these are all isotopes of each other. Okay, an isotope means we're literally all carbon, but this carbon atom for some reason has a couple extra neutrons. This one has 6 and this one has 7. So on your periodic table, the atomic mass is kind of like an average of the isotopes. So that's all isotopes mean. And we also use those in medical diagnosis. All right, last thing we're going to talk about here, and then we'll have a little unit on water, is we're going to talk about single bonds and double bonds. So when I draw something like this, this shows that there's a single bond between these two molecules. Hydrogen and hydrogen bonding or sharing a covalent, because if you look at the periodic table, hydrogen has 1 valence electron. Now, this is kind of special because hydrogen's so tiny. Here's the nucleus of its atom. It only needs to fill up the first shell. So it only needs 2 to be stable. Helium is the same way. Everything else needs 8. So he's a little bit of an exception to the rule. So they share an electron. So that's going to be a covalent bond. And here, this is a single bond. Okay? But then some atoms, like oxygen, do something different. If oxygen forms a bond with herself, because you always learn that you breathe in O2, you breathe in O2. That means you're breathing in a molecule of not just one oxygen atom, but 2 of them bonded together because they want to be stable. If you look at the periodic table, oxygen by itself is a 6, so it needs 2 more electrons to be stable. So this is also a 6. So what they have done is they've gotten together and they share 2 valence electrons. So that makes 6 plus 2, she's sharing, so she's happy. She's got 8. And this one has 6 on her own, but is sharing 2 here, so 2 plus 6 is 8, and she is also happy. So this is called a double covalent bond, right? And double just means they share 2. And then you're going to have triple. And nitrogen has a number, it has 5 regular electrons that it owns, all free and clear on its own. So it needs 3 more to be stable. So when you are dealing with N2, which is 2 nitrogens covalently bonded, they actually form a triple bond. Okay, so single, double, and triple just tells you how many electrons are being shared, and multiple bonds only occur in covalent bonding. Ionic bonding is give and take, so it's just one bond, nothing different. All right, so we've talked about our single bond, our double bond. We have talked about our salts. We've talked about our isotopes. And we are going to hold off on hydrogen bonds and van der Waals because they are super specific, and we will talk about them and why they act and behave they act on the next video.